Hello there, and welcome to Science Documentary for Sleep. Tonight, I'd like to spend some time with a familiar idea, approach gently the facts of space, and how they unfold when we don't rush them. This is a documentary-style exploration, shaped for listening as much as for watching. You can follow closely, or let the ideas pass at a comfortable distance. Nothing here needs to be memorized. Understanding often arrives slowly, sometimes later, and sometimes not at all. And all of that is fine. I'll be here as a steady presence, moving carefully from one observation to the next, letting the science speak in its own calm way. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. If you'd like, you can share where you're listening from and what time it is there right now. Let's begin. As we move forward from the opening moment, nothing shifts suddenly. The pace remains unhurried, and the setting stays wide and quiet. Imagine an immense dark plain, stretching in every direction, where almost nothing interrupts the view. No wind passes through it. No surface waits to be touched. There is simply space, vast and unoccupied, extending far beyond any familiar scale. The primary fact here is simple and precise: outer space is overwhelmingly empty. On average, the density of matter between stars is far lower than any vacuum humans can create on Earth, often just a few atoms per cubic centimeter. In many regions, even that is generous. This doesn't mean space is nothing, but rather that matter is spread extraordinarily thin. Atoms are present, yet separated by enormous distances relative to their size. That emptiness matters quietly. It shapes how galaxies evolve, how light travels, and how long changes take to unfold. As you listen, you're not required to picture the numbers. You're only observing the scale of absence. The mind doesn't need to hold on to this. It can simply rest in the openness before moving on. That sense of openness carries forward without interruption. Nothing has filled the space yet, and nothing needs to. Now imagine a faint glow crossing that vast emptiness, moving steadily, never speeding up, never slowing down. It doesn't rush, it simply goes. The central fact here is that light travels at a finite speed, about 300,000 kilometers per second. And because of this, looking into space is also looking into the past. Light from distant stars and galaxies takes years, centuries, or even billions of years to reach us. When astronomers observe a galaxy 10 million light years away, they see it as it was 10 million years ago, not as it is now. Space acts as a natural time delay. This matters because space becomes a historical record. Telescopes are not just seeing far, they are seeing earlier. You, as a listener, don't need to track timelines. The idea can remain soft distance and time are quietly linked. The thought can drift onward, carried by light that never hurries. That traveling light doesn't move through chaos. Its path is shaped gently by motion that appears calm from afar. Picture a planet circling a star, tracing the same path again and again, like a slow, careful drawing that never quite closes in on itself. There's no visible force pulling it sideways, no invisible rail holding it up. The single fact here is that orbit is a form of continuous free fall. A planet stays in orbit because it is constantly falling toward its star, while also moving forward fast enough to keep missing it. Gravity pulls inward, motion carries it onward. There is no balance point where gravity turns off. Instead, orbit is a graceful compromise between attraction and motion. This matters because it replaces the idea of support with one of motion. Nothing holds planets up. They move in a way that sustains itself. You don't need to imagine equations, just the steadiness of a path that persists without effort. The thought settles, still in motion, ready to drift further. That motion unfolds within a space that is not truly cold or warm. It exists at a quieter baseline, almost imperceptible. Imagine a faint, uniform glow filling all directions, not bright enough to see, not strong enough to feel, but present everywhere at once. The core fact here is that the universe has a measurable background temperature of about 2.7 Kelvin, just above absolute zero. This temperature comes from the cosmic microwave background, the cooled remnant of the early universe. It is remarkably uniform, meaning nearly all of space shares this same gentle thermal state. Even the emptiest regions are not at absolute zero. This matters because it tells us the universe has a shared history. Long after stars form and fade, this background remains as a quiet echo of earlier conditions. You don't have to imagine the beginning of everything, only the persistence of a faint warmth. The idea can remain soft, spreading evenly without asking for attention. Within that faintly warm emptiness, something familiar is missing. The silence there is not dramatic, it's structural. Picture an event unfolding far away, a collision, an explosion, a sudden release of energy. No matter how violent it is, nothing carries its sound outward. The single fact here is that sound cannot travel through space because sound requires a medium, like air or water, to transmit vibrations. Space is too empty for those vibrations to pass from particle to particle. Without sufficient matter, sound waves cannot form. The event happens, but silence remains. This matters because it reminds us that many human expectations don't apply universally. Space follows different rules, not harsher ones, just quieter ones. You don't need to imagine noise stopping, just the absence of something that never begins. The quiet continues naturally, making room for the next idea. That quiet is not unprotected, even in stillness. Structures exist that guide and shield. Imagine Earth surrounded by an invisible, elongated bubble stretching far into space on one side and compressed on the other. You can't see it, but it moves with the planet. The main fact here is that Earth's magnetic field creates a magnetosphere, which deflects charged particles from the sun. This magnetic shield protects the atmosphere from being gradually stripped away by solar wind. Without it, Earth might resemble Mars, which lost much of its atmosphere after its magnetic field weakened. This matters because habitability depends on subtle, unseen systems. Protection doesn't always look like walls. Sometimes it looks like guidance. You don't need to picture field lines or diagrams, just the presence of a quiet barrier. The idea rests there, stable, before gently moving on. That protection allows something steady to continue shining, not dramatically, not urgently, but reliably. Picture a star held together by its own gravity, glowing not because it burns, but because it transforms. Its surface looks calm, even though its core is active beyond imagination. The single fact here is that stars produce energy through nuclear fusion, converting hydrogen into helium and releasing energy according to well-tested physical laws. This process can continue for billions of years in stable stars like the Sun. Fusion is not an explosion. It is controlled by gravity and balance. This matters because it explains why stars are dependable on cosmic timescales. Their light is patient. As you observe this, Nothing is required of you. The fact stands on its own. The glow remains steady as the exploration continues onward. The steady glow of stars carries forward without interruption. Nothing has changed in tone, only in distance. Imagine looking at a star long after its light has left its surface, traveling calmly through space that does not resist it. The star itself may already be different, but the light continues, unchanged by what happens later. The single fact here is that starlight can outlive the star that produced it. If a star explodes or fades, the light it emitted earlier keeps moving through space until it reaches something that can receive it. This happens because light does not require its source to continue existing once it has been emitted. It carries its energy independently. This matters quietly because it means space preserves traces of events long after they are over. Light becomes a messenger that does not check back. As you listen, you're simply observing persistence without intention. The idea moves onward, carried by momentum rather than urgency. That persistence unfolds within structures that are larger than stars alone. The scale expands, gently, without sudden jumps. Picture countless stars grouped together, moving slowly around a shared center, forming a soft, rotating disk with faint arms extending outward. The primary fact here is that galaxies are gravitationally bound systems containing billions or even trillions of stars, along with gas, dust, and dark matter. Their shapes are governed by rotation and gravity over immense timescales. Galaxies are not static collections. They evolve slowly, their stars orbiting a common center much like planets orbit stars, but on far larger scales. This matters because it shows that structure emerges even in vast emptiness. Gravity organizes without instruction. You don't need to hold the numbers in mind, just the idea of many lights moving together. The motion continues, unforced, as attention drifts outward. That outward view reveals something that does not glow. It does not announce itself, but it shapes everything. Imagine watching stars move within a galaxy and noticing that they orbit faster than visible matter alone can explain. Something unseen is influencing their paths. The single fact here is that dark matter exists as a form of matter that does not emit or absorb light, yet exerts gravitational influence. Its presence is inferred from how galaxies rotate and how light bends through space. Dark matter does not interact strongly with normal matter except through gravity. It forms a vast, invisible framework around galaxies. This matters because most of the universe's mass appears to be invisible. What we see is not the majority of what exists. You don't need to picture its substance, only its effect. The unseen remains present, quietly shaping what comes next. That invisible structure stretches across distances that resist intuition. Space does not end neatly between galaxies. Picture immense filaments of matter spanning millions of light years, connecting clusters of galaxies like threads in a nearly empty tapestry. The core fact here is that on the largest scales, matter in the universe is arranged in a cosmic web. Galaxies are not randomly distributed, but trace filaments formed by gravity acting on dark matter over billions of years. Between these filaments lie vast voids with very little matter at all. This matters because it reveals order without design. Large-scale structure emerges from simple physical laws applied patiently over time. You, as an observer, don't need to imagine the whole web. A single thread is enough. The pattern extends beyond view, and the thought follows gently. Within those structures, motion continues in one dominant direction, not through space, but with space itself. Imagine every distant galaxy slowly drifting away from every other, not because they are moving through space, but because the space between them is expanding. The single fact here is that the universe is expanding. Observations show that distant galaxies are receding from us, with farther galaxies moving away faster, a relationship described by cosmic expansion. This expansion does not have a central point. It happens everywhere at once. This matters because it reframes motion. Space itself is dynamic, not a fixed stage. You don't need to imagine an edge or a destination, only gradual separation. The expansion continues quietly, without pushing or pulling attention. That expansion carries with it a subtle consequence. Over time, things grow more spread out. Picture galaxies drifting so far apart that their light becomes fainter, stretched into longer wavelengths as space expands. The primary fact here is that cosmic expansion causes redshift, where light from distant galaxies is stretched to longer wavelengths. This effect increases with distance and provides evidence for expansion. Redshift does not mean the light is tired. It reflects the stretching of space itself. This matters because it allows astronomers to measure vast distances in cosmic history using light alone. You don't need to track spectra or instruments, just the idea of light lengthening. The wavelength stretches, and the thought relaxes with it. As things spread out, change slows in a particular way. The universe does not rush toward an ending. Imagine stars forming less frequently as gas becomes thinner, with long intervals of quiet between bright events. The single fact here is that star formation has been decreasing over cosmic time. The universe was more active in the past, forming stars at a higher rate than it does now. As available gas is used up or dispersed, new stars become rarer. This matters because it shows that cosmic activity follows a long, gradual arc rather than a sudden decline. You don't need to feel loss in this, only the calm of slowing processes. The pace remains gentle, leaving space for the next unfolding idea. That gradual slowing carries forward without pause. Nothing stops. It simply unfolds more quietly. Imagine vast clouds of gas drifting through galaxies, thinner than before, moving slowly under gravity's influence. They are not empty, but they are less eager to collapse. The single fact here is that stars form when dense regions of gas collapse under gravity, but this requires sufficient density and cooling. As gas becomes more diffuse over time, the conditions for star formation become harder to meet. Cooling allows gas to lose energy and compress. Without enough cooling, collapse stalls. This matters because star formation is not guaranteed. It depends on specific physical conditions that are becoming less common. You don't need to imagine the collapse itself, only the growing rarity of the moment when it begins. The clouds drift on, and the idea moves with them. Those clouds exist within a universe where temperature changes slowly. Cooling is patient, not abrupt. Picture the universe as a whole very gradually losing energy, not by cooling like a hot object in air, but by stretching. The primary fact here is that the universe cools as it expands. As space stretches, the energy of radiation decreases, leading to lower overall temperatures over cosmic time. This cooling is uniform on large scales and tied directly to expansion. This matters because it links temperature, time, and geometry into a single process. The universe's thermal history follows from its size. You don't need to calculate temperatures, just the sense of slow, even cooling, The thought settles into that steadiness, ready to continue. Within that cooling universe, time itself behaves reliably. It does not vary with expectation, only with motion and gravity. Imagine a clock drifting through space far from any massive object, ticking calmly, unbothered by its surroundings. The single fact here is that time passes at different rates depending on gravity and relative motion, as described by relativity. Stronger gravity and higher speeds cause time to pass more slowly, relative to distant observers. In most of intergalactic space, these effects are minimal, and time flows very evenly. This matters because it shows that time is part of the structure of the universe, not a separate backdrop. You don't need to imagine distortions, only that time is quietly flexible. The ticking continues, unstrained, as the narrative drifts onward. That steady time allows matter to change form, not dramatically, but predictably. Picture atoms drifting through space, occasionally meeting, occasionally separating, governed by well-understood rules. The core fact here is that atoms formed primarily in the early universe, with hydrogen and helium making up most ordinary matter. Heavier elements formed later inside stars and were dispersed by stellar processes. This means the material around us was assembled over long periods, in stages. This matters because it ties everyday matter to cosmic history. The elements are not random, they are sequenced. You don't need to list the elements, just the idea of gradual assembly. The atoms continue their slow interactions, carrying the thought forward. Those elements drift even between galaxies. Nothing stays perfectly contained. Imagine individual atoms traveling for millions of years through intergalactic space, rarely encountering anything at all. The single fact here is that matter can exist outside galaxies, dispersed into intergalactic space through processes like supernova explosions and galactic winds. This matter becomes part of the thin medium between galaxies. This matters because it shows that galaxies are not closed systems. They exchange material with their surroundings. You don't need to imagine the journey in detail, only the openness of heaths. The atoms move on, and the idea remains light. In that openness, gravity still acts patiently. It never switches off. Picture two distant galaxies slowly influencing each other, their paths bending almost imperceptibly over millions of years. The primary fact here is that gravity operates over infinite range, though its strength decreases with distance. Even very distant objects exert gravitational influence on one another. This influence accumulates over time, shaping large-scale motion. This matters because small forces, given enough time, become significant. The universe favors patience. You don't need to imagine acceleration, just subtle guidance. The pull remains gentle, and the thought follows calmly. That patience extends to cosmic change itself. Nothing in space demands urgency. Imagine the universe continuing as it is now, for far longer than it has already existed, with gradual changes layered upon gradual changes. The single fact here is that many cosmic processes operate on timescales vastly longer than human history. Millions to billions of years are typical, not exceptional. This means most of the universe changes slowly from any single viewpoint. This matters because it reframes expectation. Stillness often hides motion that is simply very slow. You, as an observer, are not required to keep pace. The idea remains open, ready to continue its quiet unfolding. That quiet unfolding continues without any clear boundary, time passes, but nothing announces the transition. Imagine a region of space where gravity has had enough time to gather matter inward, slowly tightening its hold over long spans. Motion becomes less about drifting and more about settling. The single fact here is that gravity causes matter to clump over time, amplifying tiny differences in density into large structures. Regions that begin slightly denser than their surroundings gradually attract more matter, becoming denser still. This process is slow, but it is persistent. It does not require direction or intent, only time. This matters because it explains how structure arises from near uniform beginnings. Complexity grows from small imbalances. You don't need to imagine the beginning clearly, just the steady accumulation. The idea holds gently, letting gravity continue its quiet work. As matter gathers, shape begins to emerge, not sharply, but with consistency. Picture a massive cloud collapsing inward, not all at once, but more quickly at its center than at its edges. Motion becomes layered. The primary fact here is that collapsing matter often forms rotating disks due to the conservation of angular momentum. As material falls inward, any small initial rotation speeds up, flattening the structure. This is why disks appear around forming stars, planets, and even galaxies. Rotation is not added later. It is preserved and intensified. This matters because it shows that shape follows from motion. Disks are not designed. They are inevitable under these conditions. You don't need to track forces, only the smooth flattening of motion. The rotation remains calm, continuing forward. Within those disks, smaller systems take shape. They form quietly, without ceremony. Imagine dust grains colliding gently, sticking together, then colliding again, growing slowly in size. Nothing dramatic happens at first. The single fact here is that planets form through accretion, where small particles gradually stick together under gravity, eventually building larger bodies. This process can take millions of years. There is no single moment when a planet suddenly appears. Growth is incremental and patient. This matters because it reframes creation as accumulation. Large outcomes arise from countless small steps. You don't need to picture the finished planet, only the ongoing gathering. The grains continue to meet, and the idea moves on. That slow construction leaves traces behind. Not everything becomes part of a planet. Picture leftover debris circling a star, asteroids, comets, fragments that never fully merged. They remain in motion, unchanged for long periods. The core fact here is that planetary systems often contain remnants of formation, such as asteroid belts and cometary clouds. These are leftover material from the accretion process. They persist because conditions never allow them to fully assemble into planets. This matters because it preserves history. These remnants act as records of early conditions. You don't need to assign purpose to them. They simply remain. Their quiet orbits carry the thought forward. Some of those remnants travel very far. Their paths are long and slow. Imagine a comet drifting outward into deep space, spending most of its existence far from any star, barely changing at all. The single fact here is that many comets originate in distant reservoirs, like the Oort cloud, where they can remain for billions of years before passing near a star. Their composition often remains close to its original state from early planetary formation. This matters because comets preserve ancient material. They are among the least altered objects in a system. You don't need to imagine their return, only their long waiting. The distance stretches, and the idea stays light. Closer in, surfaces respond to gravity differently. Size changes behavior. Picture a small rocky body with jagged edges, unable to pull itself into a smooth shape. Now, imagine a much larger body, rounded by its own pull. The primary fact here is that objects above a certain size become spherical due to gravity overcoming material strength. This is known as hydrostatic equilibrium. Smaller bodies remain irregular, while larger ones smooth themselves over time. This matters because shape reflects mass. Geometry becomes a physical consequence. You don't need to judge the forms. Just notice the transition. The rounded shapes persist, steady and quiet. All of this unfolds within systems that are not isolated. Change continues through interaction. Imagine two galaxies slowly approaching each other, their outer stars beginning to feel a shared pull long before anything collides. The single fact here is that galaxies can merge, interacting gravitationally over hundreds of millions of years, reshaping their structures without immediate destruction. These mergers redistribute stars and gas, often triggering new patterns of motion. This matters because even large systems remain flexible. Scale does not prevent change. You don't need to imagine impact, only gradual influence. The approach remains slow, leaving space for what comes next. That slow approach between galaxies does not lead immediately to disruption. First, it creates subtle rearrangements that take time to notice. Imagine stars within a galaxy gently shifting their orbits, not because they collide, but because the overall gravitational landscape is changing. Paths stretch, bend, and resettle. The single fact here is that when galaxies interact, individual stars almost never collide. The distances between stars are so large that even during mergers, direct impacts are extraordinarily rare. Instead, the interaction is dominated by gravity acting on vast scales, reshaping orbits rather than causing crashes. This matters because it challenges a common image of cosmic violence. Even large events in space are often quiet reorganizations. You don't need to picture chaos, just many steady paths adjusting over time. The motion remains calm, and the scene continues without strain. As orbits adjust, gas behaves differently from stars. It responds more visibly to change. Picture clouds of gas compressing as gravitational forces shift, becoming denser in some regions while thinning in others. The primary fact here is that galactic interactions can compress gas, increasing its density and sometimes triggering new waves of star formation. Gas responds to gravity and pressure in ways stars do not. This compression can create bright regions where new stars begin to form, even as older stars continue their quiet orbits. This matters because it shows how interaction can renew activity rather than end it. Change can create conditions for new beginnings without drama. You don't need to imagine sudden brightness, just gradual gathering. The gas settles where conditions allow, and the thought moves on. Those newly formed stars inherit their environment. Their properties reflect where they began. Imagine a cluster of young stars forming together, sharing similar motion and composition, moving as a loose group through their galaxy. The single fact here is that stars often form in clusters, emerging from the same molecular cloud and sharing similar ages and chemical makeup. Over time, these clusters can disperse, but their shared origin remains detectable through careful observation. This matters because it allows astronomers to reconstruct history. Motion and composition carry memory. You don't need to track individual stars, just the idea of shared beginnings. The cluster drifts gently, and the narrative continues. As stars age, their behavior changes predictably, not suddenly, but in stages. Picture a star slowly exhausting the hydrogen fuel in its core, its balance shifting almost imperceptibly at first. The core fact here is that a star's life cycle is determined primarily by its mass. More massive stars burn fuel faster and live shorter lives, while smaller stars burn slowly and endure far longer. This relationship is well understood and observed across many stellar populations. This matters because it introduces reliability. Stellar aging follows patterns that do not depend on chance. You don't need to imagine the end of a star, only its steady progression. The timescale stretches, and the idea remains unhurried. Some stars end quietly, others do not. Imagine a massive star reaching a point where fusion can no longer support its core, gravity finally overcoming outward pressure. The single fact here is that very massive stars can end their lives in supernova explosions, briefly outshining entire galaxies and dispersing heavy elements into space. These explosions are rare on human timescales, but common over cosmic history. This matters because supernovae are a primary source of elements heavier than iron, enriching the surrounding space. You don't need to imagine the brightness, just the redistribution. The material spreads outward, and the thought follows softly. That dispersed material does not vanish. It becomes part of what comes later. Picture heavy elements mixing into surrounding gas, becoming part of future stars, planets, and other structures. The primary fact here is that each generation of stars forms from material enriched by earlier stellar deaths. The chemical complexity of the universe increases over time. This gradual enrichment makes later systems different from earlier ones. This matters because it ties cosmic change to accumulation rather than replacement. Nothing is wasted. You don't need to imagine cycles closing, just layering. The material settles into new contexts, and the idea remains open. All of this unfolds under laws that remain consistent. They do not adapt to scale. Imagine the same physical principles applying equally to atoms, stars, and galaxies, without adjustment or exception. The single fact here is that the laws of physics observed on Earth appear to operate the same way throughout the observable universe. Experiments and observations consistently support this uniformity. This consistency allows understanding to extend outward without needing new rules for each scale. This matters because it makes the universe intelligible, even at distances we cannot reach. You don't need to feel mastery here, only continuity. The laws remain steady, and the exploration continues, unforced. That continuity of physical law carries forward without emphasis. Nothing new is announced. It is simply present everywhere. Imagine a particle drifting alone through space, far from stars, far from galaxies, governed by the same rules that apply in laboratories on Earth. No exception is made for its isolation. The single fact here is that fundamental physical constants such as the speed of light, the charge of the electron, and the strength of gravity appear consistent across the observable universe. Measurements from distant galaxies match those made locally. This uniformity is not assumed. It is tested repeatedly through observation. This matters because it allows distant phenomena to be understood using nearby experiments. The universe speaks one language. You don't need to remember the constants themselves, only their steadiness. The particle continues drifting, and the idea moves quietly along. Within that consistency, space itself still changes. Its behavior is subtle, not mechanical. Picture two distant points in space, not moving through space, yet slowly becoming farther apart as the fabric between them stretches. Nothing pushes them. The primary fact here is that space-time is dynamic. According to general relativity, space and time are part of a single structure that can expand, curve, and respond to energy and mass. This is not motion through space, but change of space. This matters because it reframes what it means to move or remain still. Position becomes relative to a changing backdrop. You don't need to visualize equations or grids, just gentle stretching. The distance grows imperceptibly, and the thought relaxes forward. That stretching affects how gravity appears to act, not by weakening it, but by shaping its reach. Imagine light passing near a massive object, its path bending slightly, not because light has weight, but because space itself is curved. The single fact here is that gravity is best described as the curvature of space-time caused by mass and energy. Objects follow the straightest possible paths within that curved geometry. This bending of light has been observed many times, confirming the model. This matters because gravity becomes geometry rather than force. Motion follows shape. You don't need to picture curvature precisely, just the idea of guidance rather than pulling. The light bends gently, continuing onward without strain. In regions of extreme curvature, familiar ideas begin to soften, definitions stretch without breaking. Picture a massive star collapsing inward beyond a critical point, forming a region from which light cannot escape. Nothing marks the boundary visibly. The core fact here is that black holes form when mass is compressed enough that escape velocity exceeds the speed of light. Beyond the event horizon, information cannot reach the outside universe. Black holes are defined by simple properties: mass, spin, and charge. This matters because it shows how extreme conditions simplify description rather than complicate it. Complexity falls away. You don't need to imagine the interior. Physics itself cannot yet describe it. The boundary remains quiet, and the narrative continues. Despite their reputation, black holes are not cosmic vacuums. They do not roam, consuming indiscriminately. Imagine a black hole sitting where a star once was. Its gravitational influence is greater at a distance than that of the original star. The single fact here is that a black hole's gravity, far away, behaves like that of any object with the same mass. It does not pull in surrounding matter more strongly unless that matter comes very close. Most objects remain safely in orbit, unaffected by its presence. This matters because it corrects a common misunderstanding. Extreme objects still follow ordinary rules at distance. You don't need to feel threat or drama, just precision. The black hole remains still, and the thought passes calmly by. Over very long times, even black holes change. Nothing is truly permanent. Picture a black hole slowly losing mass, not by consuming, but by releasing faint energy over immense durations. The primary fact here is that black holes can emit Hawking radiation, a quantum effect that causes them to lose mass extremely slowly. For stellar mass black holes, this process takes far longer than the current age of the universe. The effect is theoretical but widely supported. This matters because it suggests that even the most enduring structures may fade. Permanence is relative. You don't need to imagine the radiation itself, just the patience of time. The mass decreases imperceptibly, and the idea moves on. That patience defines much of cosmic behavior. Events unfold on scales that resist urgency. Imagine the universe continuing far beyond the present era, with stars aging, galaxies drifting apart, and processes slowing further. The single fact here is that many models predict a future universe dominated by darkness and low energy, where activity becomes increasingly rare over trillions of years. This is not collapse, but quiet continuation. This matters because it frames cosmic time as open-ended rather than goal-driven. There is no deadline. You, as an observer, are not expected to follow it to the end. The future remains distant, and the exploration stays gently unfinished. That distant future does not replace the present. It simply exists alongside it in thought. Imagine the universe as it is now, still active in many places, still forming structures even as overall change slows. Nothing has ended. Nothing is closing. The single fact here is that the universe today contains regions at very different stages of evolution. While some galaxies are quiet and old, others are actively forming stars and reshaping themselves. Cosmic time is not synchronized. Different environments progress at different rates. This matters because it prevents a single narrative of aging. The universe does not move forward as one object. You don't need to imagine a timeline, just simultaneous variety. The present remains full, and the idea continues gently. That variety includes environments unlike anything familiar. Conditions change without concern for habitability. Picture a region near a neutron star, where matter is compressed beyond ordinary atomic structure, forming something dense and unfamiliar. The primary fact here is that neutron stars are formed when massive stars collapse, compressing matter so tightly that protons and electrons combine into neutrons. A teaspoon of neutron star material would weigh billions of tons on Earth. These objects are small but extraordinarily dense. This matters because it shows how matter can exist in forms far removed from everyday experience, yet still obey known physics. You don't need to picture the density fully, just the extremity of compression. The thought eases onward, leaving the surface undisturbed. Some neutron stars reveal themselves through rhythm. Their presence is marked by timing rather than light. Imagine a distant beacon flashing at perfectly regular intervals, more precise than any mechanical clock. The single fact here is that pulsars are rotating neutron stars that emit beams of radiation, observed as regular pulses when the beam sweeps past Earth. Their rotation rates can be extraordinarily stable. Some pulsars are accurate enough to rival atomic clocks. This matters because it shows that even extreme objects can exhibit remarkable regularity. Order persists under pressure. You don't need to track the pulses, just their consistency. The rhythm continues, steady and unhurried. Elsewhere, matter remains diffuse and almost unnoticed. Not all of the universe is dramatic. Picture vast clouds of hydrogen drifting between galaxies, barely interacting, barely changing. The core fact here is that much of the universe's ordinary matter exists as diffuse gas in intergalactic space, forming a thin medium that fills the cosmic web. This gas is difficult to observe directly, yet it contains a significant fraction of baryonic matter. This matters because it reminds us that prominence and importance are not the same. Quiet components still count. You don't need to imagine structure here, just presence. The gas drifts on, and the idea stays light. That diffuse matter interacts with light in subtle ways. Nothing abrupt occurs. Imagine light from a distant quasar passing through intergalactic gas, its spectrum altered slightly by what it encounters. The single fact here is that intergalactic gas can absorb specific wavelengths of light, leaving characteristic absorption lines that reveal its composition and distribution. These signatures allow astronomers to map otherwise invisible matter. This matters because it shows how indirect evidence builds understanding. Absence leaves traces. You don't need to read the spectra, just the idea of light carrying information quietly. The light continues, marked but unhindered. Across all these environments, randomness plays a role, but it does not dominate. Picture countless particles moving unpredictably on small scales, while large structures remain stable and patterned. The primary fact here is that microscopic randomness averages out at large scales, allowing predictable behavior to emerge from chaotic motion. This principle underlies much of statistical physics and cosmology. Order does not require control of every detail. This matters because it explains why the universe can be both uncertain and reliable at the same time. You don't need to reconcile the scales, just accept coexistence. The motion settles into balance, and the idea moves forward. That balance allows understanding to remain possible, not complete, but ongoing. Imagine future observers studying the universe with tools not yet conceived, still guided by the same physical principles. The single fact here is that scientific knowledge of the universe is provisional and expanding. Models improve as observations increase, but they are always subject to refinement. Understanding grows without requiring final answers. This matters because it frames knowledge as a process, not a destination. Curiosity continues without pressure. You are not asked to resolve anything here. The exploration remains open, calm, and unfinished, ready to continue when attention allows. That openness of understanding does not thin with distance. It remains present even where certainty fades. Imagine standing at the edge of what can be observed, where light has traveled for so long that it carries information from the early universe itself. The view is not sharp, but it is deep. The single fact here is that there is a limit to the observable universe, defined by how far light has been able to travel since the universe became transparent. Beyond this boundary, information has not yet had time to reach us. This is not an edge in space, but an edge in visibility. The universe may continue far beyond it. This matters because it places a natural boundary on knowledge without implying finality. Some things are simply not yet observable. You don't need to imagine what lies beyond, only the patience of light. The horizon remains quiet, and the thought moves gently on. That horizon is marked by a faint, ancient signal. It does not change quickly, or at all. Picture a uniform glow filling the sky in every direction, invisible to the eye but detectable with careful instruments. The primary fact here is that the cosmic microwave background is the oldest light we can observe, released when the universe cooled enough for atoms to form and light to travel freely. This radiation has been stretched by expansion into microwave wavelengths. This matters because it provides a snapshot of the universe at a very early stage, offering direct evidence of its past conditions. You don't need to imagine the early universe clearly, just the persistence of its light. The glow remains even, allowing the narrative to continue. Within that early light are small variations. They are subtle, but meaningful. Imagine slight differences in brightness across the background, almost imperceptible, like gentle ripples on an otherwise smooth surface. The single fact here is that tiny fluctuations in the cosmic microwave background represent early density differences that later grew into galaxies and large-scale structures. These variations are extremely small, but their influence compounds over time. This matters because it shows how large complexity grows from minute beginnings. Structure traces back to faint irregularities. You don't need to track the fluctuations themselves, only their long reach. The ripples remain faint, and the idea drifts onward. As structure grows, energy takes different forms. Not all of it is visible or tangible. Picture space itself carrying energy, evenly distributed, not tied to matter or motion. The core fact here is that observation suggests the expansion of the universe is accelerating, driven by a phenomenon known as dark energy. Its nature is not yet fully understood. Dark energy appears to act uniformly, affecting space on the largest scales. This matters because it shows that not all drivers of change are well characterized. Some influences are known by effect rather than cause. You don't need to resolve what dark energy is, only that it acts quietly. The expansion continues, and the thought stays light. That acceleration does not tear structures apart nearby. Its influence is subtle where gravity dominates. Imagine a galaxy cluster remaining bound while distant clusters drift farther away. The single fact here is that dark energy's effects become significant only over very large distances. On the scale of galaxies and clusters, gravity remains dominant. Local systems stay intact, even as cosmic expansion accelerates elsewhere. This matters because it clarifies scale. Different processes govern different ranges without conflict. You don't need to reconcile them actively, just allow coexistence. The structures remain stable, and the narrative continues calmly. Over time, observation itself improves. Tools become extensions of patience. Picture telescopes that do not just see light, but also detect particles, waves, and subtle distortions. The primary fact here is that modern astronomy uses multiple forms of observation: electromagnetic radiation, gravitational waves, and particle detections to study the universe. Each method reveals different aspects of the same events. This matters because understanding deepens through combination rather than replacement. No single view is complete. You don't need to track the instruments, only the widening perspective. The view broadens quietly, making room for more. With each added perspective, certainty remains measured. Nothing demands closure. Imagine knowledge accumulating not as answers, but as improved questions, shaped by clearer observation. The single fact here is that many open questions remain in cosmology, including the nature of dark matter and dark energy, and the full behavior of space-time under extreme conditions. These gaps are acknowledged, not hidden. This matters because it frames science as an ongoing conversation with reality. Understanding grows without needing to end. You are not required to hold these questions. They remain open, gently, as the exploration continues without pressure. That openness remains even when attention turns closer to home. The scale contracts, but the calm does not. Imagine the solar system suspended within its local region of the galaxy, moving as part of a much larger flow. Nothing here is isolated. It is simply nearer. The single fact here is that the Sun and its planets orbit the center of the Milky Way. completing one full rotation roughly every 225 to 250 million years. This journey is sometimes called a galactic year. The solar system's motion is steady and unremarkable on short timescales. This matters because it places familiar objects within a larger context of motion. Even what feels fixed is traveling. You don't need to imagine the full orbit, just the continuity of movement. The system drifts on, carrying the narrative forward gently. Within that orbit, the sun itself is not static. It moves and changes slowly. Picture the sun as a stable, glowing sphere, its surface calm compared to its energetic interior. The primary fact here is that the sun is a middle-aged star, about 4.6 billion years old, currently fusing hydrogen into helium in a stable phase that will last several billion more years. Its output changes very gradually over time. This matters because it explains the long-term consistency of conditions in the solar system. Stability can be a phase, not a permanent state. You don't need to anticipate its future, only its present steadiness. The light continues, measured and even. Around that light, planets follow predictable paths. Their motion is quiet and persistent. Imagine Earth tracing its orbit, returning to nearly the same position year after year, guided without correction. The single fact here is that planetary orbits are shaped by gravity and inertia, resulting in stable, repeating paths that can persist for billions of years if undisturbed. Small variations exist, but overall patterns remain reliable. This matters because it shows how long-term order can arise from simple rules. Repetition does not require supervision. You don't need to track angles or speeds, just the return. The orbit completes another pass, and the thought moves on. That stability allows surfaces to change slowly. Planetary histories unfold layer by layer. Picture a rocky planet cooling over time, its interior heat gradually escaping, shaping mountains, plains, and basins. The core fact here is that planetary geology is driven largely by internal heat and gravity. As planets cool, their geological activity often decreases. This process occurs over hundreds of millions to billions of years. This matters because it links planetary appearance to thermal history. Landscapes are records of internal change. You don't need to imagine tectonic diagrams, just the passage of heat. The surface settles, and the idea continues. Some planets retain thick atmospheres, others do not. Imagine gas surrounding a planet, held in place by gravity, slowly interacting with radiation and space. The single fact here is that a planet's ability to retain an atmosphere depends on its gravity, temperature, and exposure to stellar radiation. Smaller or hotter planets lose gases more easily. Atmospheric loss can occur gradually over time. This matters because it explains diversity among planets without invoking chance alone. Conditions shape outcomes. You don't need to compare worlds, just notice variation. The gases drift or remain, and the thought stays light. Beyond the planets, smaller bodies persist. They carry less weight, but long memory. Picture asteroids moving along stable paths, largely unchanged since early solar system formation. The primary fact here is that many asteroids are remnants from the early solar system that never formed into planets. Their composition preserves ancient material. They orbit quietly, rarely disturbed. This matters because they act as physical records of early conditions, preserved through lack of change. You don't need to imagine impact or threat, just endurance. The fragments continue their paths, unhurried. All of this exists within a broader galactic environment. Influence extends beyond visibility. Imagine the solar system moving through faint clouds of interstellar material, interacting gently with its surroundings. The single fact here is that the solar system passes through regions of interstellar gas and dust as it orbits the galaxy, subtly influencing the boundary of the heliosphere. These interactions are mild but ongoing. This matters because it shows that even familiar systems are shaped by external context. Nothing is completely sealed. You don't need to follow the boundary itself. The motion continues, open-ended, leaving space for what follows next. That broader context remains present even when nothing seems to happen. Motion continues, though it is rarely announced. Imagine the space between stars inside a galaxy, filled not with emptiness, but with thin gas and fine dust, drifting slowly along shared currents. It is not still, only quiet. The single fact here is that the interstellar medium, the gas and dust between stars, plays a central role in galactic evolution. It provides the raw material for future star formation and absorbs energy from stellar processes. This medium is sparse by everyday standards, yet massive in total. This matters because it shows that what appears empty is often active in subtle ways. Change does not require density. You don't need to imagine turbulence, just slow circulation. The material drifts onward, carrying the narrative gently forward. Within that medium, chemistry proceeds patiently. Reactions occur without urgency. Picture individual atoms meeting on the surfaces of dust grains, forming simple molecules, then separating again over long spans of time. The primary fact here is that complex molecules, including organic compounds, can form in interstellar space. These molecules assemble through low-temperature chemical reactions, often aided by dust grains. Such chemistry occurs far from planets and stars. This matters because it shows that complexity is not confined to warm or dense environments. Structure can arise under minimal conditions. You don't need to imagine life here, only chemistry unfolding. The molecules persist briefly or drift apart, and the idea moves on. Those molecules are carried into new systems. They do not remain isolated. Imagine a collapsing cloud incorporating existing material, including molecules formed long before the cloud began to gather. The single fact here is that star-forming regions inherit material from the interstellar medium, including pre-existing molecules and dust. New systems begin with ancient components. This means that stellar and planetary formation builds on prior chemical history. This matters because it connects generations of structure. Nothing starts from zero. You don't need to imagine a timeline, just continuity. The material folds inward, and the narrative continues smoothly. As stars ignite, they influence their surroundings. Their presence reshapes nearby space. Picture a young star emitting strong radiation, pushing back surrounding gas and carving out a cavity within its birth cloud. The core fact here is that radiation and stellar winds from young stars can heat and disperse nearby gas, regulating further star formation. This feedback limits how efficiently clouds collapse. Star formation is therefore self-limiting, rather than runaway. This matters because it introduces balance. Creation contains its own constraints. You don't need to imagine forceful blasts, just gradual clearing. The cavity expands gently, and the thought moves forward. That regulation affects entire galaxies. Small processes scale upward. Imagine many star-forming regions acting together, shaping the distribution of gas across a galaxy over time. The single fact here is that feedback from stars influences galactic structure by controlling how gas is distributed and recycled. This affects how quickly galaxies form new stars. Galaxies evolve through these cumulative local interactions. This matters because it shows how large-scale patterns emerge from repeated small effects. No single event dominates. You don't need to track the whole galaxy, just repetition. The cycles continue quietly, and the narrative stays calm. Over longer spans, patterns stabilize. Change becomes more measured. Picture a galaxy settling into a long phase where star formation proceeds slowly and predictably. The primary fact here is that many galaxies enter extended periods of relative stability, forming stars at a modest, steady rate rather than in bursts. This phase can last billions of years. This matters because it shows that equilibrium is a common outcome, not an exception. The universe often prefers moderation. You don't need to imagine stagnation, only balance. The pace steadies, and the thought continues unforced. Throughout all of this, scale remains flexible. Perspective shifts without strain. Imagine zooming out and in again, from dust grain to galaxy, without changing the underlying calm. The single fact here is that cosmic processes are interconnected across scales. Local interactions influence large structures, and large structures set the context for local change. No level operates entirely alone. This matters because it frames the universe as a continuous system rather than isolated layers. Understanding moves smoothly between scales. You are not required to hold every level at once. The view remains open, gently prepared for what follows next. That continuity across scales does not require awareness. Processes proceed whether or not they are observed. Imagine a region of space where nothing particularly notable seems to be happening. No bright stars forming, no dramatic interactions unfolding. Time still passes, and so do subtle changes. The single fact here is that even in relatively inactive regions of the universe, physical processes continue. Radiation moves, particles interact, and energy slowly redistributes. Inactivity does not mean stasis. These background processes are slow and often invisible, but they are constant. This matters because it reminds us that the universe does not pause. Change does not wait for attention. You don't need to identify the changes, just the idea that motion persists quietly. The scene remains still in appearance, while the narrative moves gently forward. That quiet persistence includes the movement of energy, not in bursts, but in gradients. Picture energy spreading from warmer regions to cooler ones, not rushing, simply following difference. The primary fact here is that the second law of thermodynamics applies universally over time. Energy tends to spread out, and systems move towards states of higher entropy. This applies to stars, galaxies, and the universe as a whole. Entropy does not imply disorder in a chaotic sense, but rather the distribution of energy. This matters because it provides direction without intention. Time gains an arrow through energy flow. You don't need to calculate entropy, just sense the gradual evening out. The energy disperses quietly, and the idea continues onward. That gradual spreading shapes cosmic futures. It does so without preference. Imagine stars slowly radiating their energy into surrounding space, contributing to a broader background that grows ever more uniform. The single fact here is that stars lose energy by emitting radiation, and this energy eventually disperses into space, contributing to the universe's overall energy distribution. Once radiated, this energy is not easily reclaimed for concentrated work. This matters because it explains why high-energy processes become rarer over time. Concentration gives way to diffusion. You don't need to imagine loss, only transformation. The radiation continues outward, thinning gently into the cosmic background. Even so, patterns can persist for long periods. Uniformity does not arrive all at once. Picture long-lived stars continuing to shine steadily, long after more massive stars have already faded. The core fact here is that small, low-mass stars burn their fuel extremely slowly and can remain stable for trillions of years, far longer than the current age of the universe. These stars represent endurance rather than intensity. This matters because it shows that longevity is built into some cosmic systems. Not everything moves quickly toward quiet. You don't need to project that far ahead. Just recognize the scale of persistence. The star continues shining calmly, and the narrative remains unhurried. As stars fade, remnants remain. They carry mass without light. Imagine a stellar core left behind after fusion ends, compact and quiet, no longer producing energy. The single fact here is that stellar remnants such as white dwarfs and neutron stars can persist for immense periods. Slowly cooling over time, they represent stable end states of stellar evolution. These objects change very little once formed. This matters because it shows that endings in space are often states of continuation, not disappearance. Matter remains reorganized. You don't need to imagine decay, just stillness. The remnant rests, and the thought drifts onward. Those remnants interact gravitationally. Light is not required for influence. Picture a dense object passing near another, altering its path slightly through gravity alone. The primary fact here is that gravity operates independently of luminosity. Dark or faint objects can still shape their surroundings through mass. This allows unseen matter to play an active role in cosmic structure. This matters because it reminds us that visibility is not a measure of importance. Influence can be silent. You don't need to identify the objects, just their effect. The paths bend gently, and the narrative continues. Across all of this, the universe remains patient. It does not resolve quickly. Imagine cosmic processes continuing far beyond the span of any single observer, layered across timescales that do not compete. The single fact here is that the universe accommodates processes operating simultaneously on vastly different timescales, from subatomic interactions to galactic evolution. These processes coexist without conflict. This matters because it allows understanding to remain partial without being incomplete. No single view captures everything. You are not expected to keep pace with all of it. The perspective stays wide, open, and gently prepared for what unfolds next. That wide perspective remains steady as attention drifts outward again. Nothing pulls it abruptly. Imagine looking across the universe not as a sequence of events, but as a landscape where many processes unfold at once. Some are fast, most are slow, and none require an observer to proceed. The single fact here is that the universe does not have a single dominant timescale. Different physical processes operate independently, each according to its own constraints and conditions. Atomic interactions occur in fractions of a second, while galactic evolution spans billions of years. This matters because it explains why the universe can appear both active and still at the same time. Motion depends on where you look and how closely. You don't need to reconcile these scales. Simply noticing their coexistence is enough. The view remains broad, allowing the next idea to arrive gently. Within those overlapping timescales, randomness plays a limited role. It is present, but not overwhelming. Picture particles moving unpredictably at microscopic levels, while larger structures retain stable forms and patterns. The primary fact here is that while quantum processes involve inherent uncertainty, large-scale cosmic behavior is highly predictable due to statistical averaging. Randomness smooths out over large numbers and long times. This is why planetary orbits, stellar lifetimes, and galactic motion can be described reliably. This matters because it shows how predictability emerges naturally, without suppressing uncertainty at smaller scales. You don't need to choose between order and randomness. They coexist comfortably. The motion continues, settled and untroubled. That predictability allows space to be mapped and measured, not perfectly, but effectively. Imagine astronomers charting positions and distances using repeated patterns, motions that repeat, signals that arrive steadily. The single fact here is that cosmic distances are measured using standardized physical relationships, such as stellar brightness, orbital dynamics, and expansion rates. These methods build a consistent scale of the universe. Each measurement depends on others, forming a connected framework. This matters because it turns vast distance into something intelligible. Scale becomes relational rather than abstract. You don't need to remember the methods. Only that measurement is possible. The map extends outward, calm and continuous. With measurement comes perspective. Position becomes relative, not absolute. Picture Earth as one moving point among many, without central privilege or fixed reference. The core fact here is that there is no special center in the universe. Observations show that large-scale expansion looks the same from any location. This principle, sometimes called cosmological homogeneity and isotropy, means the universe has no preferred viewpoint. This matters because it removes hierarchy from position. Location does not imply importance. You don't need to imagine disorientation, only a quality of perspective. The point of view remains calm, uncentered, and open. That openness allows systems to overlap. Influence extends without ownership. Imagine radiation from distant stars passing through regions where it has no lasting effect, then subtly altering matter far away. The single fact here is that energy and information can traverse immense distances without regard to boundaries like galaxies or systems. Space does not partition influence cleanly. Light, particles, and gravitational effects move freely across regions. This matters because it shows the universe as permeable rather than segmented. Processes interweave gently. You don't need to trace paths, just the sense of continuity. The influence passes through, leaving the idea quietly intact. Over time, interactions accumulate, not dramatically, but persistently. Picture countless small gravitational influences adding together, gradually shaping trajectories over millions of years. The primary fact here is that cumulative effects, especially gravitational ones, can produce large changes over long durations, even if each individual interaction is weak. This principle underlies much of cosmic structure formation. This matters because it emphasizes patience over intensity. The universe favors accumulation. You don't need to watch the change happen. Just allow time to do its work. The paths adjust slowly, and the narrative continues. All of this unfolds without conclusion. Nothing is aiming to finish. Imagine the universe continuing as a system of ongoing processes without a final state required for understanding. The single fact here is that physical laws describe how things change, not where they are meant to end. The universe does not progress toward a prescribed outcome. This matters because it frees understanding from expectation. Observation does not need a destination. You, as a listener, are not asked to resolve anything. The thought remains open, balanced, and gently prepared to continue whenever attention returns. That lack of a prescribed ending allows attention to soften. Nothing needs to resolve in order to continue. Imagine the universe not as a story moving toward closure, but as a field of processes unfolding side by side. Some grow, some fade, most simply persist. The single fact here is that many cosmic processes are cyclic or ongoing rather than linear. Matter moves through different states: gas, star, remnant, gas, again without a final form. This cycling is driven by physical conditions, not by progression toward an outcome. This matters because it reframes change as circulation rather than advancement. The universe reuses rather than replaces. You don't need to follow a cycle from beginning to end. Just notice that motion often loops. The idea stays loose, allowing the next observation to arrive gently. Within those cycles, energy takes recognizable paths. It does not disappear, only changes form. Picture energy released from a star spreading outward, warming nearby matter, then radiating away again into space. The primary fact here is that energy is conserved. In all observed processes, energy changes form: radiative, kinetic, thermal, but the total remains constant. What changes is its availability to do work. This matters because it grounds cosmic behavior in continuity rather than loss. Transformation replaces vanishing. You don't need to track the accounting, only the persistence. The energy continues its quiet transitions, and the thought moves forward. As energy spreads, contrast diminishes, differences slowly soften. Imagine a region once shaped by intense activity gradually blending back into its surroundings, becoming harder to distinguish. The single fact here is that over long time scales, gradients in temperature, density, and energy tend to smooth out. Extreme contrasts are temporary in cosmic terms. This smoothing does not erase structure immediately, but it reduces sharp boundaries. This matters because it explains why dramatic events leave subtle long-term traces. Intensity fades into context. You don't need to imagine erasure, only blending. The region becomes less distinct, and the narrative drifts onward. Even so, information can persist longer than form. Patterns remain detectable after sources fade. Picture ripples traveling outward long after the initial disturbance has ended. The core fact here is that information about cosmic events can persist in radiation, particle distributions, or gravitational effects long after the events themselves are over. Astronomers often study remnants rather than active processes. This matters because it shows that the universe records itself. Evidence lingers without intention. You don't need to reconstruct the event, just acknowledge the trace. The signal continues outward, thinning but present. That persistence allows observation across time. Distance becomes a kind of archive. Imagine light from many eras arriving together, layered by the time it took to travel. The single fact here is that because light travels at a finite speed, observing distant objects reveals the universe at earlier stages. Different distances correspond to different cosmic times. Space therefore functions as a natural record of history. This matters because it allows understanding without travel. Time is accessible through observation alone. You don't need to arrange the layers, just notice their coexistence. The light arrives quietly, carrying its age without announcement. Across these layers, simplicity often reappears. Complexity does not always increase. Picture regions where matter is sparse, interactions are rare, and behavior is governed by a few dominant forces. The primary fact here is that in very low-density environments, physical behavior can become simpler, dominated by gravity and radiation rather than complex interactions. Such regions make up much of the universe's volume. This matters because it counters the idea that complexity must always grow. Simplicity returns naturally under certain conditions. You don't need to prefer one over the other, just allow both. The environment remains spare, and the idea moves on. That balance between complexity and simplicity remains unresolved. It does not seek resolution. Imagine the universe as a system where detail accumulates in some places while dissolving in others, without overall preference. The single fact here is that cosmic evolution does not move uniformly toward greater complexity or greater simplicity. Both trends occur simultaneously in different regions. This coexistence is stable and persistent. This matters because it allows multiple narratives to be true at once. No single direction dominates. You, as an observer, are not required to choose one view. The perspective remains open, steady, and ready to continue without pressure. That openness remains even as attention becomes quieter. Nothing narrows, it simply softens at the edges. Imagine the universe not as something unfolding in front of you, but as something already in motion, continuing whether it is watched or not. Stars form, fade, and drift without pause. The single fact here is that cosmic processes are not dependent on observation. Physical events occur independently of whether they are measured, recorded, or noticed. Observation reveals behavior, but it does not initiate it. This matters because it separates understanding from control. The universe is not performing, it is proceeding. You are present as a witness, not a requirement. That distinction settles gently, allowing the narrative to move forward without effort. Within that independence, regularity still appears. Patterns repeat without rehearsal. Picture the predictable return of orbital motions, the steady ticking of atomic transitions, the reliable spread of light. The primary fact here is that many physical processes are governed by stable, repeatable relationships. These regularities allow the universe to be described with consistent models. Without such regularity, prediction would not be possible. This matters because it explains why long-term understanding can exist at all. Stability underlies explanation. You don't need to track the repetitions, only the sense of reliability. The rhythm continues, unforced and quiet. That reliability does not imply rigidity. Variation exists within constraint. Imagine two stars of similar mass forming in the different regions. following the same basic rules but ending with slightly different outcomes. The single fact here is that while physical laws are fixed, initial conditions vary, leading to diverse results even under the same governing principles. This balance produces both predictability and diversity. This matters because it shows how uniqueness arises naturally. Difference does not require exception. You don't need to resolve the differences, just acknowledge them. The outcomes diverge gently, and the idea moves onward. Across vast distances, isolation is common. Contact is the exception, not the rule. Picture a single star traveling through space with no nearby neighbors, separated by distances that prevent interaction. The core fact here is that most stars are separated by immense distances, making direct interactions rare. Much of the universe consists of systems evolving independently. Isolation is a default state on cosmic scales. This matters because it reframes the universe as spacious rather than crowded. Separation shapes behavior. You don't need to imagine loneliness, just distance. The star continues on its solitary path, and the narrative stays calm. Yet even isolated systems are influenced indirectly. Nothing is completely detached. Imagine faint gravitational effects accumulating over time, subtly altering motion without direct contact. The single fact here is that long-range forces, especially gravity, allow distant objects to influence one another over extended periods. Influence does not require proximity. This matters because it balances isolation with connection. Distance reduces immediacy, not relevance. You don't need to trace the force, just the persistence of influence. The paths bend slightly, and the thought continues. Over time, these subtle influences shape large patterns. Change becomes visible only in retrospect. Picture a galaxy's shape altered over hundreds of millions of years by accumulated interactions that were individually insignificant. The primary fact here is that many large-scale cosmic structures result from the accumulation of small effects acting over immense timescales. No single moment defines the outcome. This matters because it emphasizes duration over drama. The universe builds quietly. You don't need to witness the change, only accept its timescale. The structure holds, shaped by patience. That patience extends to understanding itself. Clarity emerges gradually, if at all. Imagine knowledge forming not as answers arriving, but as questions becoming more precise over time. The single fact here is that scientific understanding advances incrementally, refining models rather than completing them. Each improvement narrows uncertainty without eliminating it. This is not a failure of knowledge, but its nature. This matters because it removes pressure from comprehension. Partial understanding is still understanding. You are not required to settle anything here. The thought remains open, calm, and gently ready to continue. That readiness to continue does not require momentum. It exists even when movement slows to near stillness. Imagine the universe at a moment when no dramatic event is unfolding nearby. No stars are exploding, no galaxies are colliding, yet space is not inactive. The single fact here is that even in the absence of large events, fundamental processes like particle interactions, radiation flow, and gravitational influence continue everywhere. There is no true pause in physical activity. Stillness is a matter of scale, not of cessation. This matters because it reframes quiet moments as active in their own way. Absence of spectacle does not mean absence of process. You don't need to identify what is happening, only that something always is. The calm holds, making space for the next observation. Within that constant activity, balance often emerges, not perfectly, but reliably enough. Picture opposing influences, expansion and gravity, heating and cooling, counteracting each other across long spans of time. The primary fact here is that many cosmic systems reach states of dynamic equilibrium, where opposing processes balance without stopping. Stars, atmospheres, and galaxies often persist in such states for immense durations. Equilibrium does not mean nothing changes. It means change is regulated. This matters because it shows how stability arises naturally. Without freezing motion, persistence is an active condition. You don't need to imagine a fixed point, just sustained balance. The system holds steady, and the narrative continues gently. That balance allows patterns to remain recognizable. Form endures even as details shift. Imagine a galaxy maintaining its overall shape while individual stars move, age, and disappear within it. The single fact here is that large-scale structures can remain stable even though their components are constantly changing. The identity of the structure does not depend on permanence of parts. This is common across cosmic systems. This matters because it separates continuity from sameness. Persistence does not require immobility. You don't need to track individual changes, just the enduring outline. The form remains quietly accommodating motion. Across that enduring form, cause and effect remain local. Influence does not spread instantly. Picture a change occurring in one region of space, its effects taking time to reach elsewhere, carried only by finite speed signals. The core fact here is that no information or influence travels faster than light. Causality is preserved across the universe by this limit. This constraint shapes everything from communication to cosmic structure. This matters because it imposes order without control. Limits make relationships coherent. You don't need to imagine messages traveling, just the patience built into connection. The effect moves outward at its own pace. That pace creates separation between events, not disconnection, but spacing. Imagine distant regions of the universe evolving independently, simply because not enough time has passed for them to affect one another. The single fact here is that many regions of the universe are causally disconnected from each other, meaning they cannot influence one another within the current age of the universe. This is a result of finite signal speed and cosmic expansion. This matters because it shows how independence arises naturally. Separation does not require barriers. You don't need to imagine isolation emotionally, just physical distance in time. The regions continue, unaware of one another. Even so, common rules still apply. Consistency does not require contact. Picture two distant galaxies that have never interacted, yet evolve according to the same physical principles. The primary fact here is that universal physical laws apply uniformly, even across causally disconnected regions. Similar processes occur without coordination. This suggests that the universe is coherent without being centralized. This matters because it reinforces the idea of shared structure without shared history. Unity does not depend on interaction. You don't need to imagine coordination, just parallel unfolding. The systems evolve separately, yet familiarly. Taken together, these observations do not close a picture. They leave it open, by design. Imagine the universe not as a completed explanation, but as a continuous setting where understanding can enter and leave without urgency. The single fact here is that scientific descriptions of the universe remain intentionally open-ended, describing behavior accurately without claiming final completeness. This openness is not uncertainty, it is precision without excess. This matters because it allows curiosity to remain calm. Knowledge does not need to finish in order to be true. You are not expected to hold everything together here. The perspective stays wide, quiet, and unfinished, ready to rest or to continue whenever attention returns. As this exploration eases to a pause, there's nothing that needs to settle into memory. Some ideas may stay close, others may drift away, and both are natural responses. The universe does not ask to be held all at once, and understanding does not require completion. You may feel alert, or quietly reflective, or simply neutral, and all of those states belong here equally. What we've touched on remains unfinished by design, continuing beyond this moment, whether it's being considered or not. The facts of space are patient. They do not mind when attention moves elsewhere, and they remain available whenever curiosity finds its way back.